Okay, great. Yeah, thanks so much for coming to my talk today. Yeah, this is based on a series of joint works with John, Jerry, Alan, and Aaron. Yeah, let's get started. So, okay, so this series of works was motivated by like a couple of theoretical oddities and perhaps like places where the analysis of existing theoretical algorithms for solving linear inverse problems had some shortcomings. So I'll use the first third of the talk to maybe give some brief overview of the state of the art, like what is known for sparse recovery and matrix completion, and also what new things our algorithms bring to the table. And then I'll use the second third of the talk to sort of like highlight a particular structural aspect of our proofs that I think I'm curious to see if it will have implications in other settings, and I think it's particularly self-contained, so hopefully that part will be the only part with a proof. And then I'll use like the last third to like very briefly sneak in our generalization to the matrix completion setting. Okay. So let's talk about sparse recovery. So in sparse recovery, we want to solve an under-constrained linear system. So in particular, I imagine you have n observations of a hidden variable, n linear observations, and n is much less than d. So this is clearly impossible in the worst case, and you need to assume something more about your problem. And the typical structural assumption people make in the sparse recovery literature is that the planted solution x star is sparse. Here you should think of s as a parameter that's much less than d. Okay. So what about algorithms for solving this problem? Well, a sort of a minimal assumption you need about the problem formulation is that A doesn't contain any sparse-ish vectors in its kernel. So in particular, if it has a 2s sparse vector in its kernel, I can move in that direction and create another sparse solution. So this is called the restricted null space property. And it's sort of been known for like decades at this point that under this assumption, with particular some parameterization of R and P, the convex programming relaxation of minimizing the L1 norm subject to matching all the constraints solves the problem in polynomial time. Okay, and this is a very like desirable algorithm in many ways. So it's very flexible. It generalizes to noisy settings just fine. And it uses essentially minimal assumptions about the problem. All you need is that A satisfies R and P. But the only downside, although I know like many in this room are like working hard to alleviate even this downside, is that it's potentially expensive in high dimensions to run a generic convex programming solver. Okay. On the other hand, if you assume something stronger about A, that it satisfies this thing known as the restricted isometry property, or RIP, which basically means that not only does it not contain sparse vectors in its kernel, it like really preserves it's like a near isometry on all the sparse vectors. So for any V with O of S non-zero entries, it roughly preserves the L2 norm of V. You can actually design near linear time algorithms. Basically in this setting, there are many different approaches to make it work. You could do greedy algorithms, you can do non-convex algorithms, you can do like projected gradient descent type algorithms, and these all run in near linear time under this RIP assumption. Okay. So in theory, under standard generative models, like for example, if you assume A has IID rows drawn from some reasonable ensemble, both work just fine. And in general, like these attain faster runtimes. But in practice, it seems that based on like real data sets people care about, a variety of works have reported that these fast methods seem to be much more brittle in terms of like, is the assumption actually satisfied? So what's going on here? And our investigation of this problem sort of started by noticing that these convex programming-based polynomial time algorithms are very robust under a natural semi-random adversary we introduce. In particular, even if you perturb the instance by the semi-random adversary, which I'll define momentarily, the algorithms continue to work just fine. However, in the near linear time setting, this RIP assumption and a variety of structural assumptions used by these fast algorithms are immediately broken by the adversary we introduce. Okay. So I want to take a quick aside here to like pitch this notion of a semi-random model. It's not a general like one-size-fits-all definition, but in general, here's the philosophy behind semi-random models. So it's sort of a way of interpolating between the worst case and the fully random best case scenario in statistical algorithms. So in a lot of these statistical settings, if you make no assumptions, structural assumptions on your problem whatsoever, it's usually like very hard or maybe even information theoretically impossible to solve the problem. But if you assume certain like nice properties about your problem instance, like maybe it's IID or fully random in some setting, then all of a sudden you have these like very fast polynomial time algorithms. And semi-random models are sort of a way of testing an algorithm's overfitting to its problem assumptions. So it's asking what happens in this intermediate regime where you don't have like the fully best case assumption, but maybe you still have enough information in your instance to solve the problem information theoretically. Can we design algorithms which compete with the ones that work in the fully random setting? So sort of the motto is, if everything works when life is easy, but we want to solve problems maybe where life isn't so easy, we want to design an algorithm that is the most robust to the structural assumptions we're actually using in the problem. Okay. Oops. So yeah, now I'll introduce our like instantiation of this philosophy in the setting of sparse recovery. So recall that here is the setting. You have n linear measurements of a S-sparse vector, and in the nearly linear time algorithms, they typically assume that A has this nice property that it preserves sparse vectors approximately. Okay, so the basic semi-random adversary we introduce is the following. So you imagine your matrix is not fully RIP. It contains like a planted RIP matrix, so some subset of the rows are nice. And then an adversary comes and gives you like additional consistent information. So they're not lying to you what AI times XR is. They are really telling you the truth. But they're just making this assumption that your matrix is fully RIP violated. Okay, so here's the full definition. You take an RIP matrix, you add some additional consistent measurements, and then I just shuffle it so that you don't know which ones are the real are the random ones and which ones are the semi-random ones.
What fraction of rows can you?
Yeah, so I'll get to that shortly. I mean, our algorithms will work for any fraction of rows, but they actually get better the more rows you assume are like random versus semi-random. Okay, so I just want to remind the audience that like we haven't really changed the information theoretic or even like the polynomial time solvability of this problem, because you can still solve the convex relaxation. Like in particular, note that by giving additional rows, I can't like decrease the size of the kernel, right? So it still satisfies RNP. But you know, you can probably guess the next thing I'm about to say. This sort of semi-random adversary can arbitrarily hinder the RIPness of a matrix. So in particular, you can construct explicit counterexamples where like many greedy or non-convex iterative methods like immediately fail. And furthermore, these convex iterative methods seem to, like projected gradient set, seem to rely on some sort of like restricted problem conditioning, which is also very easy to break using this semi-random adversary. Okay, so what's our first result is you can solve these planted RIP matrices, sparse recovery problems in them in near linear time. So I'm hiding one detail, which is that you do have to assume that sort of the matrix doesn't have any too large entries, but in typical models, you can, this is just true in basically any standard RIP construction I know, and you can just sort of drop any row that is obviously semi-random. Okay, so you might not be satisfied with this result. Like for example, like, okay, I'm assuming AXR is exactly equal to B. What happens if I add some noise? As Santosh asks, what happens if I like actually give you like a larger fraction of RIP rows? Like, can I kind of recover the rate given by like the information theoretically minimum number of rows? And then also like this notion of PRIP seems like quite like structured. It's like, where in real life are you going to encounter someone who just hands you some real random rows and someone who hands you some non-random rows, right? And fortunately, we have another theorem that sort of addresses all of these simultaneously. I'm going to like maybe not focus too much on it, but just note that we give a recovery rate that depends on the noise in some instance optimal way. And then our algorithm also has a runtime that interpolates between the fully random case and the semi-random case. So if I give you n rows and n is much larger than the information theoretically minimum, like s, then I still run an st time. Also, yeah, we generalize the notion of an adversary to handle weights. So I'm not going to spend too much time on this particular slide, but I just want to give you a sense of the flavor of results we were able to attain. Okay, so that's sparse recovery. And then, like any good TCS researchers, we solve the vector problem. We ask, all right, what about the matrix problem? So here's a natural generalization of this problem to the matrix setting. You could just define your hidden vector to be a matrix, and then you define like linear measurements through matrices, right? So this is a problem studied in like phase retrieval among other things. And the natural generalization of sparseness is just oh yes, question.
Sorry, maybe you can repeat the question. I don't have a microphone.
Oh yeah, sure.
So I think in this, before we move on,
Yes.
I think there is some kind of like when you have ill-conditioned matrices, there is still like a computational statistical gap, like polynomial time versus exponential time algorithms. If the matrix was ill-conditioned.
So I mean, you can always solve this guy in polynomial time.
Sorry, when you have noise. When you have
noise, you can kind of like relax this constraint to have some L2 error, and this will also just work fine.
But I thought in the noisy case, the recovery that you get from the convex program doesn't match the best exponential time algorithm.
Yeah. So okay. Yeah. So I'm hiding some slight like yeah. So you depend on like sort of like the worst coordinates of the noise. So like among the worst rows in your matrix. So yeah, there's some sort of like even tighter instance optimality that you can go for, which I'm not going to talk about here.
So is this like matching the convex program or the exponential?
Yeah, this is matching the convex program. Yeah.
Okay.
Cool. Okay. Yeah, so matrix sparse recovery. So the natural, I'm just gonna like quickly skip over this because I'm not gonna talk about it too much, but basically the natural way of formulating this is instead of assuming that your planted solution is sparse, you assume it's low rank, which is like spectral sparsity. And then you also require sort of like at least dr observations just by a dimension counting argument. To give you a rank R matrix in D dimensions, I need dr parameters. Okay, so we actually did not work on this problem, but at NeurIFS 2023, you can ask Xing Gao and Yu Chung, who recently posted a paper called Robust Matrix Sensing in the Semi-Random Model, which generalizes our algorithm to this setting. Okay, so what was our team working on? Our team was working on a specific case of this, which has arguably incomparable assumptions to matrix sensing, matrix completion. So this is famously piloted by like, I think it's made famous like in the TCS community at least by the Netflix challenge and sort of understanding algorithms for solving it. But the setting here is that the observation matrices are like very interpretable. They just correspond to like a particular entry of your hidden matrix, right? So given roughly dr random observations of the matrix, can I recover the matrix, right? Okay. So the thing to note about the matrix completion setting is that some sort of RIP type assumption is sort of impossible. So what do I mean by a RIP type assumption? Recall that an RIP assumption is like a for all type statement. It's saying for all sparse vectors, these observations sort of preserve the vector, right? But here, if you try to make this sort of statement for all rank R matrices, the observations sort of preserve the matrix. Like this is clearly false because if you show me some observations, I'm just going to like hide a spike where you missed it, and you can't tell me anything about that observation, right? So what sort of things can people do in this setting? So you have to kind of make an additional structural assumption, which is that you dodge this kind of worst case behavior. And typically, the way this is phrased is the row and column spans of X star are spread in some way. They don't place too much mass on any particular coordinate. So this is known as incoherence. Yeah, the technical definition doesn't matter too much, but basically it means that it doesn't favor any coordinate too much. Okay. So under these assumptions, what do people know how to do? So in polynomial time, the natural thing one would try is to solve the min nuclear norm solution instead of like the min L1 solution. And after a long series of works, Rech in 2011 shows that roughly dr samples are able to make sure that this convex program actually does recover the matrix under this incoherence assumption. Okay. What about in near linear time? So the state of the art that doesn't have dependencies on other, like more than logarithmic dependencies on other problem parameters like conditioning is due to Jane and Netropoli in 2015. And they showed that by using some kind of like clipped projected gradient descent, you're able to get an algorithm that it takes more samples than the polytime algorithms, but it runs much faster. Well, in some parameter regimes, dr to the 7 time. Okay. Okay, so you might look at these. This is also under incoherence, and you might look at these results, and immediately two things might pop out. So these rates, while good, are still not quite as good as we can do in polytime, and also. Yeah, so this assumption of incoherence, like why is this the right assumption? Can we say anything when it doesn't satisfy incoherence? And interestingly, a third axis of the state of the art in matrix completion is the noise robustness of these algorithms. So suppose instead I give you observations from M star, a rank R matrix, plus some Frobenius norm-bounded noise. Well, actually, even the polynomial time algorithms, we don't know how to output a rank R solution that is more than root d times delta away from the truth. So this, I'm not personally aware of any barriers to removing this root d factor. So this is like a question, interesting question, even polynomial time. Okay. So our results is best phrased in 2 stages. So the first stage of our results is given a rank R matrix M star. Note that I make no assumptions about incoherence or anything like this. Plus some Frobenius norm-bounded noise. I can give you a matrix M that recovers M star to error O of delta. Not quite. It recovers it to error O of delta on a 99% by 99% of all rows and columns. So yeah, this is actually the first sort of results of this nature we were aware of in the literature. And it's saying like, the price of dropping this spread assumption is that, well, some of the coordinates aren't going to be good, but if you just remove a few very bad coordinates, you can still get roughly optimal guarantees. Okay, and we do this using dr samples, hiding a subpolynomial factor, and dr squared time. Okay, so that's part 1. And then in part 2, we show how to boost this partial completion result to full results, assuming some sort of like spread assumptions on the subspace. So we introduce this new notion called regular subspace. This is satisfied by random subspaces with high probability. We're able to take roughly the same sample complexity and time and lose a little bit in the accuracy, but it's still like poly R rather than root D. And then finally, under the standard assumption, our samples and time go up by like roughly a R factor. Okay.
The matrix is not actually low rank, right?
The matrix we output is also low rank.
It is?
You can kind of just project to the rank R subspace and lose only a constant factor in the distance.
Wait, it's still gonna be rank R, or you blow up the rank?
No, like given a rank larger than R matrix, if I just truncate it to rank R, this almost doubles the distance to ops. Okay, cool. Okay, so yeah, wow, that took longer than I was expecting. Okay, so I'll try to show you one proof. I think this is like a cool takeaway from our work and sort of inspired the entire line of work. So yeah, so in when you first, like this is an observation-minded audience, when you first saw the RIP definition, you might be like, oh, this sounds kind of like well-conditioning, right? In fact, it's like some sort of restricted well-conditioning. So for example, if I told you the support of X star, it really is a well-conditioned problem, right? I just need to like restrict to that set. Okay, so I can actually do you one better. If you assume your matrix is RIP, it's actually well-conditioned on a larger set of vectors called numerically sparse. So roughly speaking, these are things that have a bounded L1 to L2 ratio. The proof is via some simple like shelling argument. I will go into it now. Okay, so you know, you might see this, and then a plan starts forming in your head, and maybe the plan looks something like this. So it sounds like if we just make sure that our iterates lie in this set, and then we do something else, then we win. Okay, well, yeah, how do you do that? Well, I can't tell you how to do the second line, but I can tell you how to do the first line, which is maybe you want to maintain some L1 projection, right? This at least makes sure that the top is bounded, right? And the question is sort of, in this framework, how do you reason about the effect of this L1 projection? Okay, so this is where our key geometric insight comes into play. So the punchline is sort of, if you hit a unit vector v with a random Gaussian matrix, all directions other than v are flat. Okay, so what does that mean? So suppose you have so I'm going to abuse notation and let the rows of A be like 1 over root n AI. If you hit V with a random Gaussian matrix, so all the AIs are IID Gaussian. Okay, so I'm going to write each AI in the following way. I'm going to decompose it into the V direction and then into all the orthogonal directions. And the thing to note is that AI transpose V, like it really accumulates in the V direction because you get this psi squared term, but everything else is basically random, right? And if I average a bunch of these, well, it'll definitely pick up the V direction, but it'll sort of not favor any particular other direction. And in particular, this other vector is essentially random, so it's L infinity bounded. And it's not hard to convince yourself that the trade-off is roughly 1 over root n times maybe root log v. Okay, so a little more formally, here's the statement. If you have an RIP matrix A with parameter S, and you hit V with A transpose A, there exists a short flat decomposition of the results. So there exists a decomposition to PV and EV. P is like the progress direction. It's L2 norm bounded by roughly what V was. And E is the error direction, but it's L infinity bounded. And this will let us quantify the effect of L1 projection. Okay, so a quick overview of why projected gradient descent works, armed with this new insight. So suppose for simplicity, we're in this regime where x minus x star, so x star is our target vector, is L2 norm bounded by 1 and L1 norm bounded by root s. Okay, case 1 is that actually its L2 norm is, so our goal here is just going to be like to have the L2 norm. So case 1 is actually like, it was better than I thought, and then we're just done, right? But in the second case, if the L2 norm is large, then we're just going to use A transpose AV as a descent direction. And, and the point is that this is a good idea by the lemma. So informally, it's because you can write it into the progress direction, which is where you actually want to go. And then you have this error term, which is filtered out by the L1 projection. And this is by Holder's inequality. Okay, so I'm gonna maybe like skip over this a little bit, but the idea is you start by drawing an L1 ball around your current point. If you're numerically sparse, if you're not numerically sparse, the only reason you could have been not numerically sparse is because the denominator got smaller than you think it is. And that means you have the L2 radius and you can move on. Otherwise, we can run some PGD. And okay, so yeah, it's just projected gradient descent. And the thing I want to alert your attention to is that the one step we check, which is that the progress direction was really good, and the descent direction has a short flat decomposition. This is like this fully makes sense in the semi-random setting as well. And this is sort of like the only thing we need for our algorithm to make progress. So in the semi-random setting, the idea is we're just going to maintain some weights on the rows. Note that by choosing the weights to be the random rows, I can recover like the thing I was supposed to do. But then you can just solve some convex optimization problem to make sure that this line passes. And we show how to do that in near linear time using some SGD. Okay. Okay, so this is like for the optimization experts in the room, which is like many of you, like this is probably the only talk I can get away with a slide like this, so I'm just gonna go ahead and do it. Ignore my shamelessness. Okay, so if you've seen any like PGD proof at all, it probably goes something along the lines of this. You have the progress term, which is how much closer you're getting to the target. And then you have these two terms. So this is like the descent direction, and then this is some like proximity term. Okay, and the idea is we're going to break this this descent direction down into xt minus x star and xt minus xt plus 1. And we're further going to define, we're going to break down the gradient term into the short part and the flat part. So this is the flat part, and this is the short part. And the point is, by restricted well conditioning, this term is big, right? It's saying that because xt minus x star is a numerically sparse direction, I will make progress. Okay, what about everything else? This is flat, and this is L1 bounded. Boom, Holder. This is L2 bounded, and then this is Cauchy-Schwarz / Youngable. Boom, bounded. All right, that's the whole proof. Okay, so yeah, with the last 5 minutes, I will talk a little bit about matrix completion. Yeah, so in matrix completion land, what would be the right way of defining a short, flat decomposition? So a natural thing to try is first write down the gradient, right? The gradient is sort of like the residuals of the current matrix along the observations. So basically, you want to take your current matrix, subtract off the truth, which you can see on some observations. I'm denoting the observations by omega. And then you like rescale it by 1 over p. P is the observation probability to sort of like make sure it's unbiased. So this is like the natural descent direction one might try in gradient methods. Okay. So the natural thing one might try to do following the outline in the sparse recovery case is to write this as the sum of a short term and a flat term. So formally, consider decomposing this into the progress direction. So if we just took the progress direction m minus m star, we would immediately land where we wanted to. And then the goal is to show that the residual matrix, the error term, is flat. So flat here means like spectrally flat, L infinity bounded, in other words, op norm bounded. Okay. So I show you a matrix like this, and I ask you to control the operator norm. You might think, all right, that sounds like matrix Bernstein is the one for the job. And matrix Bernstein controls the, so you can write this as sort of like a sum of d squared random matrices. Each one corresponds to a single entry. Okay. And matrix Bernstein requires 2 parameters. It requires a entry-wise bound, so like sort of a probability 1 bound on your random matrices. That in this case, it corresponds to every entry being small. And then it also requires a variance bound. So you can work out the calculation. Roughly speaking, the variance bound in matrix Bernstein corresponds to every row and column of m minus m star being small. Okay. Okay, so of course this is not true in general because again, like single spikes totally ruin this. But it's actually totally okay if you drop like 1% of rows and columns. So the point is, how many rows can be larger than like 100 times the average, L2 squared norm? Maybe like 1%, just Markov, right? Okay, the one that's like a little bit harder to see is the entry-wise bound, but you can show that for any rank R matrix, it can't have too many disjoint large entries, or else this would violate the nuclear norm. So you can also get away with dropping like 1% of rows and columns for that one. Okay, so then like, why is the paper like 50 pages long? It's because, then you have to like go back and recover these dropped rows and columns. And also like in matrix land, you can't like, in vector land, if you have a S-sparse vector or a D-sparse vector, you can still do things in O of D time. But if you don't maintain that your iterates are low rank in the matrix case, you can't even like do efficient computation. So you have to kind of like make sure that your matrices ranks don't blow up either. So that's for a later talk. Okay, and then yeah, so more generally, I'm curious about like how much this like structural setting where you really use the structural characteristics of your problem to analyze the effect of the noise, and then use some sort of geometry to filter that out. I think it's an interesting general framework for semi-random inverse problems and inverse problems in general. I'm also curious, like, sort of what types of harder adversaries we can push our algorithm to tolerate. So matrix completion gives like a slight augmentation of this like for all type statement, where it's like it's more like per matrix you give some guarantee, but I'd be curious how far we can push the envelope in terms of the adversary. Okay, thank you.
Thanks, Kevin. We have time for a question. Well, I have a question. Do you note empirically that these algorithms are robust to these real data situations that you started the talk with than COSAMP or
right. You might notice that like this is written by like 5 theorists. Like that's the next step, and we're in talks to try to make this happen. But the answer is no at the moment. But I'd be really excited if I have some experts in the audience who would be interested in exploring this framework for real data, which was the original motivation for the problem.
Oh, yes.
When you actually run the algorithm in practice, what does it boil down to? You're maintaining.
Yeah. So
just repeat the question.
Set of rows that you think are like bad.
So importantly, the set of rows we think is bad in each iteration is changing, iteration by iteration, because verifying RIP is NP hard.
Yeah.
And
you're not going to actually find the RIP.
No. So it's like in each iteration, we're going to find some subset of rows that currently works, and like this might change iteration by iteration, but the point is in each step here. So replace 1 over n with some sort of like reweighting of the rows. Any weight that works, we're just going to take the step, A transpose AV reweighted by these W's. And if you take that step, the fact that you pass these shows that you make progress. So the entire computational game boils down to finding these weights. And we give an algorithm that doesn't near linear time, but there's certainly room for practice.
So if I passed you like a straight RIP matrix, it would probably just do exactly the same thing. The weights are just staying uniform.
Yeah. So like if it was truly random, like my intuition from the proofs is just that like the W it'll output is uniform, and then you just keep taking that step.
Thank you. Let's thank Kevin again and all the speakers this afternoon.